Students, in our last video, we spent some time understanding gases and the 3 assumptions of an ideal gas and then the 5 applications of those assumptions. And so we spent a lot of time trying to understand how a gas would behave so that we could predict it in the future. In this lesson, we're going to be talking about one of the most important ways that we can detect a gas, and that is through gas pressure. Most gases are colorless and odorless. Many are unreactive. You can't see them, you can't smell them. Most gases just exist like the air around you right now, and you're primarily unaware of it. And so gas pressure is a way to measure the behavior of a gas so that you can know what the gas is doing. So it's a measurable way to describe the gas. So when we talk about gases, we spend a lot of time on pressure. So before we get into specific of gas pressure, I want to talk just about pressure in general. So you can see the guys on this slide. The guy is laying on a bed of nails, and I don't know if any of you guys have had the chance to lay on a bed of nails before. At science centers, they often have like a bed of nails for you to lay on. I've done it before. It's kind of cool. And the thing is that laying on a bed of nails while uncomfortable is not really painful. And that's because your area of your body is spread out so that there's not a lot of force as you press down on the nail. There's not a lot of force on any one nail. Imagine the difference between laying on a bed of nails and stepping on a nail. It would be much more painful to step on a nail because you would have the same amount of force, that's your body, the same amount of force, weight, but the area would be much smaller in the sense of stepping on a nail. And so that very small area would create a large amount of pressure and it would hurt. It would puncture your skin. We're laying on a bed of nails like this guy is, the force is spread out over a larger area, and so the pressure is much smaller, and so now the bed of nails is uncomfortable, but not creating enough force to puncture the skin. Gases create pressure, and they do so by colliding with the container walls. So we said yesterday that gas particles move rapid, constant, and randomly, and that their collisions are elastic. And what that means is as the gas particles in this room are running around rapid, constant, randomly, they collide with the walls of the room and they bounce off with just as much energy as they came in. So they bounce off and then they bounce off the next wall and they just keep going and bouncing around the room. And so because of that, you start to get this pressure on the walls, pressure on you. When you change your atmospheric pressure, a good visual for this is if you've ever taken a sealed bag of potato chips up into altitude, up to the mountains or something, and as you go up the mountain, the bag of chips seems to expand because the amount of gas on the inside is the same, but the pressure on the outside is getting less as you go up into the atmosphere. So as we go up in elevation, our pressure gets less, the air gets thinner, we say, but it's not really thinner, it's just there's less of it. And so we get less collisions with the bag, less pressure on the bag, so the bag seems to expand. Gases create pressure, and that's how we can understand gases. When we talk about gas pressure, that leads us directly to something called atmospheric pressure. So you and I live in Earth's atmosphere. And what the atmosphere really means is it's a whole bunch of gases that are trapped near the surface of the Earth. These gases create a pressure on us, the people, on the grass, on the walls, on the roofs of our houses. These gases create a collective pressure by running into us. You are constantly being bombarded with oxygen and nitrogen particles, and those oxygen and nitrogen particles have a mass, and they have a force and they hit an area of your skin, and that creates a pressure on your skin. Even though you're not really feeling it right now, you actually are under pressure. Gravity contains these forces and traps them here near the surface of the earth. And so we call this pressure that the atmosphere puts on us atmospheric pressure. So the atmospheric pressure is made primarily of nitrogen and oxygen. Those are the biggest components of gases within our Earth's atmosphere. And so the oxygen and nitrogen are bombarding us, they run into us, and they create a pressure. And this is a picture of kind of what we're measuring, a diagram. So 1 atmosphere of pressure is a 1 meter column of air. So a 1 meter squared column of air. And so this is 1 meter by 1 meter, but then all the way up to the edge of the atmosphere with the force of gravity pulling down on it. We call that amount of pressure 1 atmosphere. And it's also known as 101.3 kilopascals or 101,300 pascals. And like Pascal's triangle from geometry, same concept, same person. And so these are measurements of atmospheric pressure. We will often use 101.3 kilopascals and also 1 atmosphere as the units of pressure that we most often use in this course. So measuring atmospheric pressure has been something that has been of interest for quite a while. Measuring atmospheric pressure or barometric pressure actually gives you some information about the weather, about storm predictions and whether or not storms are coming in. And so one of the things you'll hear in a weather forecast will be something like the barometric pressure is dropping or the barometric pressure is rising, and that's an indicator to the meteorologists about what's going to be happening with our storms as we move forward. Well, a barometer was invented by Evangelista Torricelli over here, and this is basically what a barometer is. And so it's a small tube, and it's in a bath of mercury. And so inside of this space up top is a vacuum. There's no air in there, so there's no air pressure in there. It's a vacuum, so you'd have to remove the air from the tube and then fill it with mercury, put it upside down into this container. And what happens is, as the pressure from the earth collides with the mercury in the tub, the mercury in the container, it's going to force the mercury around and up into the tube. And as gravity pulls down, it's going to pull down the tube. The stronger the barometric pressure, the higher in the tube the mercury will be. So when there are more gases in the air, you're going to see a push of the barometric pressure rising. And if there's less gases in the air, less temperature, maybe less collisions, whatever the cause is, less collisions with the surface, then you're going to see the barometric pressure drop. And so this is a barometer. And what happens is that under normal conditions, like standard conditions, what we see is that the mercury balances at 760 millimeters of mercury. So we have 101.3 kilopascals, we have 1 atmosphere of pressure, we have 101,300 pascals, and now we can add to that another measurement of 760 millimeters of mercury is also a measurement of the pressure. So even though that seems like it's a length measurement, it's measuring the pressure because it's measuring the height of the mercury in a barometer. So we have come to standard pressure. Standard pressure is considered to be 101.3 kilopascals, which is 1 atmosphere of pressure or 760 millimeters of mercury. Now, the truth is that in any lab across the world, these values could fluctuate slightly. And so when we take a measurement, we typically record the temperature and the pressure when that measurement is taken. In most labs, we try to keep these pressure temperature readings at standard temperature and pressure. So we've mentioned that standard pressure is 101.3 kilopascals, 1 atm, or 760 millimeters of mercury. But standard temperature is 0 degrees Celsius or 273 Kelvin. And I know we haven't gotten into Kelvin yet, so for now you can just call it 0 degrees Celsius. but we represent these two values as STP, or standard temperature and pressure. And although we're not going to use STP until next chapter, I wanted to take the time now to start you thinking that pressure and temperature are always measured when we measure anything about a gas. I have given you 3 different standard pressures, and the fact is that across the globe, different regions, different countries, different areas are going to measure pressure in different units. And so just like we learned how to convert meters to feet and feet to inches and inches to miles, we also need to convert from millimeters of mercury to atmospheres to kilopascals. So the good news is that these are only ever single-step conversion factors. You can always directly convert, so they're not particularly tiring to do. They're not particularly difficult, but I do want to go over 2 different examples just to make sure that you understand how you could use standard pressure in order to do pressure conversion. Problem, it reads, the height of a mercury barometer measures 700 millimeters of mercury. What is the pressure in kPa? So I'm converting from 700 millimeters of mercury to kPa. So the first thing I need to do is write what I'm given as a fraction over 1. Now, as you know, I'm going to cancel the units that I don't want to the bottom of the next fraction, and I'm going to put the units that I do want, that I'm looking for, on the top. So in this case, that will be kPa. Now I need a conversion factor, something that makes millimeters of mercury equal to kilopascals. And for that, I want to take a second and go look back at my standard pressures. So our standard pressures are 1 atmosphere, 101.3 kPa, and 760 millimeters of mercury. So these are the very numbers that I would use for my conversion factor. So with millimeters of mercury, I will plug in 760, and for kPa, I'm going to be plugging in 101.3. Now all that's left to do is to plug this into my calculator. 700 times 101.3 divided by 760, 93.30 kPa. And that tells us the pressure in kilopascals when our mercury is reading 700 millimeters of mercury. Okay, let's try the next one. The pressure is 150.91 kPa. What is that same pressure measured in ATM? So I've started with my 150.91 kPa as a fraction over 1, and kPa cancels to the bottom. I've moved atmospheres to the top because that's the unit that I'm looking for. Now I check my standard pressures and I see that 1 atmosphere is equal to 101.3 kPa. I'm all set up, and now all that's left is to plug this into my calculator. 150.91 divided by 101.3. And I get 1.49 atmospheres. And you might ask yourself, does 1.49 seem to make sense to myself? Well, if my standard pressure is 100 about kilopascals and I'm at 150, I'm 1.5 about of my pressure. And so it makes sense that comparing my 1 atmosphere, I'm also about 1.5. So you can do that kind of comparison just to make sure there maybe aren't any mistakes in your math. I mentioned very little math in the chapter. This is actually it. These pressure conversions are the only kind of math that I'm going to be asking you for on the test. The rest is conceptual. So it's important that you understand, what is a barometer measuring? What is standard pressure? Why do we care about pressure? Those are the kinds of questions that will be asked for more points on the test. So it's important that although you do review the math, you also understand the concepts that we're presenting. All right, guys, I will see you in class.